So now that we've talked about partial derivatives of a function, we have a sense of how to differentiate functions of more than one variable. So if you recall, there's a very important differentiation rule for functions of one variable, and that's the chain rule. So in one variable, the chain rule goes like this. Suppose that y is a function of u, and u is a function of x. Then if I want to take the derivative of y with respect to x, so go from the dependent variable all the way down to this independent variable, skipping this intermediate variable, then what do? Well, I first take the derivative of y with respect to u, then multiply by the derivative of u with respect to x, like that. Or in other words, f prime of g of x, what I mean is the derivative of f of g of x is, well, it's the derivative of f evaluated at g of x, and then I multiply by the derivative of the inside, g prime of x. So this is sort of the Leibniz notation. This is more the traditional function notation, but that's what the chain rule says in one variable. So what about the two variable case? Well, the problem here is that we might mean different things by the two variable case. So case 1 goes like this. Z is a function of x and y. X is a function of t, and y is a function of t. This is sort of like the chain rule in one variable, except now we have two intermediate variables that depend on this independent variable t, and z is the dependent variable that depends on all of them. So what is the derivative of z with respect to t? So I have a dependent variable that really just depends on the independent variable t, but I have these intermediate variables. Well, it looks like this. So first, I take the partial of z with respect to x, and now notice I have to use partial here because there's some ambiguity about what I mean by the derivative of z. I could take the derivative of z with respect to x or y. So here I take it with respect to x, and then multiply by dx dt. And I'm using the regular d here because there's no ambiguity about what independent variable x depends on. It's just a function of t. So that's just like the one variable case, but I've ignored y. Well, what do? I just add. The chain rule in multivariable, I just add all of the different possibilities. So I add taking the other choice. I take the partial of z with respect to y, and then multiply by dy dt, like that. So this is what the chain rule says in the two variable case in case 1, where the intermediate variables x and y just depend on one independent variable t. So I told you about case 1, where the intermediate variables just depended on one independent variable. But now let's talk about case 2. Case 2 gets more interesting. So let's say again z is a function of the two intermediate variables x and y. So I'm saying intermediate because x and y are not going to be independent. X and y are going to actually themselves depend on two independent variables, like this. And you can see where this could get sort of endlessly complicated as we go to more and more variables. But this will be the case we'll consider. Z is a function of the two independent variables, or the two intermediate variables, x and y. And then those intermediate variables each are functions of the independent variables s and t. So now I have a choice. If I want to take the derivative of z with respect to an independent variable, I have to say what I mean. Do I mean s or do I mean t? So in that case, when I have the ambiguity, I need to use the partial derivative. So partial derivative of z with respect to s, well, I just have to consider the contribution from x and the contribution from y. So I have partial z, partial x, partial x, partial x, s plus partial z, partial y, partial y, partial s. So notice I'm taking the derivative with respect to s, and so I need to consider both contributions from the intermediate variables x and y. So here's x and here's y. But x and y themselves, I need to differentiate with respect to x. And if I wanted to take the partial with respect to t, then I have partial z, you could probably guess it at this point, partial x, partial t this time, and then plus partial z, partial y, partial t. So what about more variables? Well, I'm not going to actually write down, any more explicit formula, but I'm going to tell you a general principle. And I hope that you kind of think about this and maybe even write down the case for 3 variables. But for more variables, you just add the appropriate terms. And what I mean by that, if you had another intermediate variable, say z, well then you would just add on the contribution from that variable. And this is just one of those things where you just think about it and wrap your head around it, and it's very natural. You just sort of keep adding these partial derivative factors for all of your intermediate variables and for each one of your independent variables. So there's one thing in Calc 1, and I'm not saying this is the only thing, but it's definitely something that was a little bit unjustified when you talked about it. And what that is implicit differentiation. And now with the multivariable chain rule, we're actually in a position to give a justification for implicit differentiation. So the idea with implicit differentiation is that you didn't have y as a function of x. You had y was an implicitly defined function of x. So you can actually write a setup for implicit differentiation like this. You have an equation that looks like this. I get everything on one side. Now notice I have not solved y as a function of x because maybe I'm not able to do that. Maybe remember like x squared plus y squared equals 1. Y was not an explicit function of x. Y could only be defined as an implicit function of x. So here, if I have an equation like this, and I want to find dy dx, well, what can I do? Well, let's say that y is a function of x. Let's just pretend that y is a function of x. Then we're actually in a setup, and we'll say x is also a function of x, like that. Now, of course, x is equal to itself, so this is a little silly to write, but I just want to set it up in the setup of the multivariable chain rule. I have these two intermediate variables, x and y, that depend on the independent variable x. So what does the multivariable chain rule tell me? It tells me that the partial derivative with respect to x of xy times dx dx, so that's the derivative, this is like partial f partial x times dx dx, so in other, this is a little weird to write dx dx, but I'm saying x depends on itself, so it's just x, so it's just 1, and then I add the partial with respect to y times dy dx, okay, because the intermediate variable y depends on this independent variable x, and then that's going to be 0. But this is just 1, of course, dx over dx, and I can actually just solve for dy dx. dy dx is just minus, so I'll subtract this over, fx over fy. So this not only justifies implicit differentiation, it actually makes it a little bit simpler, because we can use this idea of partial derivatives. Whereas, if you recall, implicit differentiation had a lot of algebraic manipulation. But now it's so easy. Now we just get everything on one side, take the partial with respect to x, then take the partial with respect to y, just take the quotient, that's dy dx. All right, so here we have a perfect setup for the multivariable chain rule. So we want to know dz dt. But first, let's just note that dx dt is equal to 2t, dy dt is equal to 1 over t. Okay, so then dz dt is going to be, all right, the contribution from x, so partial x, not partial x, partial z, partial x, and then times dx dt, plus partial z, partial y, and then times dy dt. Okay, so what is partial z, partial x? Well, that's just going to be 2x. And then dx dt is 2t. And then partial z, partial y is 2y times 1 over t. But now we want our final answer to just be a function of t. But recall that x is just t squared, and y is just natural log of t. So this is really, so 2 times 2, t squared times t, so 4t cubed plus, then we have 2, y is natural log of t, and then divided by t. So that's dz dt, right there. All right, so this is a rather involved problem. We have two intermediate variables, x and y, a dependent variable z, which is just x over y, and then two independent variables, s and t. Okay, so let's just go ahead and write down what some of these things are. So partial z, partial x is just 1 over y. Partial z, partial y is negative x over y squared. Okay, what else? Partial, it's sometimes easy to make the partials look like 2's. partial x partial s is just square root of t. Partial x partial t is s over 2 root t. And here I actually mean to. Partial y partial s is t over 2 root s. And then partial y partial t is equal to root s. Okay, so there's all the possible partial derivatives that we're going to need, 6 in all. So let's look here. Partial z partial s, recall, is we just kind of take the combinations we need. So we need to look at first the intermediate variable x, and then we multiply by partial x partial s, and then plus we look at the next intermediate variable y, and we're looking for the derivative with respect to this independent variable s. Okay, and now let's just fill in what we know. So partial z partial x is 1 over y. Partial x partial s is square root of t. And then partial z partial y is negative x over y squared times partial y partial s is t over 2 root s. Okay, so let's actually fill in what x and y are. So y is t root s. So we're going to have root t over t root s plus, okay, negative, I guess I can just write minus, x is s root t, and then y squared is t squared s, and then times t over t root s. Okay, so what do we have here? Well, this is going to be 1 over, I am left with the square root of t on bottom, so square root of ts, and then minus, s cancels, one of the t cancels, another square root of t cancels, minus 1 over 2 square root of ts, which is actually just equal to 1 over 2 square root of t times s. All right, so now let's look at partial z partial t. Okay, so what is it? Just by definition, well, we look at the two intermediate variables, partial z, partial x times partial x, partial t, plus the other intermediate variable, partial z, partial y, partial y, partial t. Okay. Now what does that equal? Just plug in what everything is. So we have partial z, partial x, which is just 1 over y. And then partial x, partial t is root t. And then partial z, partial y, that's minus x over y squared times partial y, partial t is, oh, hold on a second, partial x, partial t is up here. That's not correct. Yeah, so partial x partial t is s over 2 root t. And then partial y partial t is just root s. So let's plug back in what x and y are. So this is s over y is t root s. So this is going to be 2t root s, and then root t coming from here. Yeah, so y is this is y, and then we have a 2 root t. And then plus or minus, x is going to be s root t times root s, and then all over y squared again, which y squared is equal to t squared s. Okay, so then what do we have? We have, here we're going to have a root s on top, so square root of s divided by 2t root t, and then minus, here the s's will cancel there, we'll have a, let's see, that's just going to be, well, we can just leave this as root ts all over t squared, like that. And that's good enough. So there is the partial z partial s right here, and then partial z partial t is right here. So you look at this question, you say, wait a second, this is just a Calc 1 question. And you're exactly right, but now remember we have some justification for implicit differentiation, and we also have a really slick way to do it. So what I'm going to do is I'm going to say f of x, y, is x squared y plus y squared x plus tan xy. Now why do I do that? Because if you recall what we said about implicit differentiation, dy dx is just minus the partial derivative of this with respect to x divided by the partial derivative of this function with respect to y. But this is a walk in the park. The partial derivative of this with respect to x is going to be 2xy plus y squared plus, well, we're going to get a secant squared, and then we differentiate with respect to x, so we'll get a factor of y. And then all over the partial with respect to y, which is just x squared plus 2xy plus, this time we'll take the partial of the inside with respect to y, so we'll get x, and then secant squared xy. And we're done. And now if you don't believe me that this is a refreshing, well, forgot a negative. Yeah, so if you don't believe me that this is a really refreshing way to do this, try to take the derivative here, find y prime, just using implicit differentiation as you did in Calc 1. And what you're going to see is that you're going to have a bunch of dy dx's that you're going to have to kind of combine together. You're going to have to do some algebra, subtract things over. This is a lot slicker using the techniques using these partial derivatives. Okay, so this is sort of a related rates-like problem. Okay, but we can actually use the multivariable chain rule to sort of set it up in a nice way. So the first thing we need to remember is, okay, well, what in the world is the volume of a right circular cone? Well, you can look it up or just believe me that the volume is 1/3 the base of the right circular cone, so it's going to be a circle, so pi r squared, and then times the height, h. And now what we know here is that dr dt is radius increases by 3 inches per second, so 3, and then dh dt is going to be 2. The height increases by 2 inches per second. And so we want to know dv dt. But the chain rule says that dv dt is partial v partial r dr dt plus partial v partial h times dh dt. Okay, so what's partial v partial r? Well, that's just going to be 2/3 pi r h, and then dr dt is 3. Partial v partial h is 1/3 pi r squared times dh dt, which is 2. Okay, now we just want to plug in 3 for r and 12 for h. We'll have 2/3 pi times 3 times 12 plus times another 3 plus 1/3 pi times 3 squared times 2. And so what do we have? We have 2 times 3 is 6, times 12 is 72. This is just going to be 3 times 2, so it looks like 78 pi, and our units will be inches cubed per minute.